In this video, we'll be talking about triangle congruence theorems, and these are the ones that work for proving two triangles are congruent. So SSS stands for side, side, side. So that's where you have three pairs of corresponding congruent sides. So that looks like this, where the two sides here they correspond with each other and they're congruent. These two sides are congruent, and then these two bottom sides are congruent. Now, they don't always have to line up like this. You could have two triangles that are congruent by side, 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 like this, where you have one pair of congruent sides, a second pair of congruent sides, and that third pair of congruent sides is actually this side that they share along one edge. So it can show up in different ways, but side, side, side is three sides that are all marked as congruent. Now, side angle side really has to do with where that angle that is congruent is placed. So with SAS, you have something that looks like this. Now, the key thing is that the angle that's marked as congruent is where the two sides that are marked as congruent come together. So this side here and this side here meet at this angle, which happens to be the angle that's marked as congruent to this angle over here. So it would not be SAS, for example, if you had these sides marked as like so, and then you had, say, this angle marked down here. So it's really important that the angle that's marked as congruent is between the two sides, SAS. And here, like, these angles aren't really between the two sides. This angle is, you could say, it's like touching this side, but not the other one. So it's not really in between them. It's sort of just hanging off on one end over here. So SAS really the angle that's marked has to be in between those two. Oh, here, let's get rid of them. Has to be between the two congruent marked sides. Same thing sort of applies with ASA, or angle side angle. So here, same idea, but now you've got two angles that are marked. So maybe something like this. And the side that's marked has to be the one that sort of connects the two angles that are marked. So something like this and this, right? So again, if you had this situation, this would not count as ASA because the side that's marked doesn't connect the two marked angles. It touches one of them, but not the other one. So to be ASA, the side that's marked has to be in between or touching the two angles, like both of the two angles that are marked as well. Okay, that brings us to angle, angle, side. So these two are really similar because they both have two angles and a side that are marked. Now, kind of like we already saw, ASA has that one side in between the two angles, like we just said. Whereas in angle, angle, side, this guy, now you're dealing with a situation where two of the angles are marked and the side that's marked is not in between them. So it is only touching one of those angles. So that might look something like this, where that third side is hanging off on the edge down here and only touching this one angle in that bottom right. Or it could look like this, where these two sides are marked. But again, that marked side is only touching one of the angles that's marked. It's not touching both of them. And so it's not really in between them like it is over here in this one. So that's angle, angle, side. These two, again, are really easy to mix up. So you really want to pay attention to, like, is that side touching just one of the angles, or is the side touching both of the angles? And that's kind of a good rule of thumb for determining whether it's ASA versus AAS. All right, and then that brings us to hypotenuse leg. Now, hypotenuse leg is a sort of special case type of theorem that only applies to right triangles. So you think about, where have you heard the word hypotenuse before? Maybe in the Pythagorean theorem, or when you talk about right triangles. So you really need to see that the triangle has a 90-degree angle in order to apply hypotenuse leg. So here, basically what it's saying is if you know the triangle has 90 degrees, then you can look at, okay, if one of the legs is marked and the hypotenuse is marked, then you can say that the two triangles are congruent. So in a way, this is kind of like side angle, like because we've got a side and then another side, and then the angle that's marked is that 90-degree angle. Like in a way, it's like that, which side angle does not usually work to prove triangles are congruent, unless it's this special case where you're talking about right triangles. So those are all of the triangle congruence theorems that do work to prove that triangles are congruent. So now we'll talk about some that do not work. So angle is one that you'll see as like a trick. So you might see something like this, and it'll ask you, are these two triangles congruent? The answer is no. The reason is triangles can have the same degree or measures of angles, but one could be way bigger than the other, and the angles would still be congruent and match up. So angle is a theorem that proves triangles are similar but not congruent. And last but not least, we have SSA, or side angle. We've already alluded to this a little bit, but here is where you have two sides and an angle, but the angle that's marked is not in between the sides, it is only touching one of the sides. This is a case where you cannot conclude that the two triangles are congruent at all. It just doesn't, you don't have enough information to be able to say that the triangles are fully equal. Okay, so that is all of our triangle congruence theorems. Now, when you are proving that two triangles are congruent, sometimes all the markings are going to be given to you, like you see in all of these pictures I've drawn, which these are pretty simple examples. But other times, it won't be so easy to tell exactly what's congruent and what's not congruent. And here's where you really have to rely on your previous geometry knowledge to help you. For example, you might see a problem like this that tells you that these two sides are parallel. Let's just call this A, B, C, D. So it might tell you that AB is parallel to DC. It might give you some sort of a diagonal like this. And it might also tell you that, I don't know, let's say angle A is congruent to angle C. So here, just looking at this, so far, all we're given is one angle. Angle A is congruent to angle C. That's the only congruent marking we know. Parallel means something totally different than congruent, so we don't even know if AB is the same as DC. They may be, but we don't know. So you really have to rely on what you're given, the information that's given in the problem. And specifically, whenever you have parallel lines with a transversal, you have alternate interior angles, where this angle here is congruent to this angle down here. They're on opposite sides of the transversal. They're in between the two parallel lines. Those are alternate interior angles, so they must be congruent. And we can conclude that because we know the lines are parallel. So it's not told to us that those angles are congruent, but we can use our logic to determine that. Another thing we can say is that segment DB is congruent to itself. This is a common side, kind of like I mentioned earlier, so we can give it a congruent marking and just say that that one side is the same for both triangle ABD as it is for DCB. And so with this information now, we've got this red angle A marked with this red angle C. We've got this blue angle ABD marked as congruent to this blue angle CDB. And we have this one side in the middle marked as congruent. All together, we've got two angles, angle, and a side. And that side, you have to ask yourself, is it angle, side, or angle, side, angle? Well, is the side touching both of those angles or just one of them? So in this case, DB touches, if I just look at, say, this triangle above, that side DB touches the blue angle, angle ABD, but it doesn't touch the red angle A. So it's really only touching the one angle. So I can say it's not really in the middle, it's not between the two angles, or whoops, it's not here, it's not in between them, it is only touching one. So I would say that these two triangles are congruent by angle, angle side. So again, and I would say angle or triangle ABD is congruent to triangle CDB. And again, you want to make sure you're matching up your angles correctly there too, but that's for another video. All right, so some other just real quick ways that you can find congruent angles and congruent sides to help you in proving triangles are congruent. You can look for vertical angles. This is a really big one. If you see two triangles that look something like this, then right away mark those vertical angles as congruent. That can be an extra set of angles that you know are congruent to each other. Alternate interior angles, like we just saw. If you know that two lines are parallel, then you know that you have alternate interior angles there. Angle bisectors. So if the problem tells you that, say you have something like this, let's say it says AD bisects angle, let's give these some letters. Let's say it bisects angle CAB. Well, to bisect something means to cut it in half. So if I look at angle CAB right here, and I imagine that it's getting cut in half by AD, then that will mean that CAD, one half, is congruent to BAD, the other half. So look for angle bisectors. If it's told using that word, bisects, you have to explicitly be told that something is bisecting an angle. Same thing goes for segment bisectors. You see these a lot in sort of these types of problems where you might see that like AD bisects segment CB. So if AD bisects segment CB, then AD is the thing doing the cutting, CB is the thing that's getting cut in half, so CB is getting bisected into this segment and this segment. Those are the two halves of segment CB, and we can say those are congruent. Same goes for midpoints. You see this a lot with something like this, where you might be told that B is the midpoint of segment AC. A midpoint is halfway in between, so that would tell you that these two segments are congruent. Common sides we've already talked about, although sometimes they're not as obvious, where you may have two triangles that overlap with a common side like this, where you're trying to show that this blue triangle is congruent to this red triangle, and the common side they share is this guy here, where those two colors overlap. Same goes for a common angle. Sometimes you have two triangles that overlap, something like this, where the blue triangle, say here, overlaps with this red triangle here, and they share that angle in common. So you can say that that angle is congruent for both the blue triangle and the red triangle. It's like it's congruent to itself. All right, so those are some of the things to look out for when you are trying to mark segments and angles as congruent. But remember, you can't just go marking things willy-nilly. You have to have a good reason for why you're marking something as congruent. It's got to be told that it's a bisector, or you have to be able to, or be told that the lines are parallel, or some of them are visual. Like visually you can see that the angles are vertical angles, they're across from each other. But in any case, these strategies are really helpful for finding congruent sides and congruent angles that can then help you use these triangle congruence theorems.